Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Anas and I am going to present about my final year project, which is the design and the development of smart thermoelectric system for small scale cooling application. I am being supervised by Dr. MOTAKABBER. Okay. In this presentation, we are going to go through 6 outlines, which is the introduction, the literature review, the methodology, the results and analysis, the conclusion, and also the reference. Okay, now we move on to the introduction. Okay, what is a Peltier module? A Peltier module is basically a heat pump, which is it will absorb heat on one side and will release it on the other side. This happens when voltage and current is supplied to the module. It will instantaneously heats up on one side and it will cool down on the other side. This is caused by the movement of electron between two different energy levels in a dissimilar semiconductor. The heating happens when the electrons are going from a high energy state to a low energy state, causing the electrons to release their energy in the form of heat. And also vice versa, when the electrons are moving from a low energy state to a higher energy state, the electrons will absorb the energy also in form of heat. It will absorb heat, which makes it cool. So why are we going to use particular? Why do not we use the conventional vapor compression cooler or the CVC cooler? This is because the Peltier cooler are very low in maintenance and low in noise because it does not have any moving parts in it. It is also very small in size. Only some of it have a 4 cm by 4 cm size, and we do not have to use any cooling agent for it to run efficiently. But for the CVC cooler, it is very high has high maintenance, and it is very noisy because of the compressor in it. It is also very large and bulky system, and it is prone to gas leakage because it uses cooling agent. So what can the Peltier be used in what application? The Peltier cooler can be used for a small refrigerator or in an ice box because it can contain both cold and hot side, and we can store food in it. It also can be used as a temperature control device to control sensitive electronics like a processor, because the temperature control of the Peltier cooler is very sensitive. Okay, now for the objective. What is our objective for the research? Basically, the first one is to design and develop the PID based controller system, thermoelectric cooling system. The second one is to implement the design thermoelectric cooler module for small scale cooling system, and the last one is to study and compare the performance of our design system with other similar works, which will be in the literature review. So for the problem statement, the problem with a Peltier cooler is that the efficiency is very poor because it has a very large surface temperature gradient, because the cold side and the hot side is very near to each other. The second one is that the control system of the circuit can cause the efficiency to become worse because the control system can draw power more than it needed. And lastly, it is not the Peltier cooler is not fully portable because of its high power consumption. So it cannot be used on a battery for a long time. So okay, now we move to the literature review. So the theory that the thing that we are going to focus on this research is that the coefficient of performance. So what is coefficient of performance? The coefficient of performance, or COP, is the energy being absorbed, which is the Q cold, over the supply power. So if the COP of Peltier cooler is generally low because of its high power usage. So in order for us to increase the COP, we need to increase the usable energy, which is the QC, while maintaining the input power. So this is the formula that we are going to use to calculate the COP of our system. The thing that the most important thing in this formula is the QC and also the P, which is in the left side bottom of the slide. Okay, now we move on to the methodology. This is the research flowchart, which is the first in FYP1 we start picking our title from the coordinators and write a literature review about 15 papers. and then we are going to find the benchmark papers, and after that we are going to design the peltier cooling system itself. So in FYP2 we are going to test the system and check for its COP to make sure that the COP is meet our requirement, and we are going to make any adjustment so that it will become will meet our requirement in terms of the COP. So this is the proposed design. The proposed design that I propose, which is as we can see, the peltier module is being sandwiched by two heatsink with a fan. One it is inside in the cold side, and one is in the hot side. In the hot side is being used to dissipate heat that is from the TAC module, and from the cold side is for to circulate the air inside the insulated box so that it can be cooled more efficiently. The peltier module is going to be controlled by the PID controller, and the PID controller is going to control the temperature inside the insulated box by using the temperature sensor, which is the thermocouple sensor, which acts as a feedback signal to the PID controller. This is the circuit with using real components that, as we can see here. So now we move on to the system flowchart. So the system will work on AC, which is going because the PID controller works on AC, and the PID controller will control the power to the TEC module and the fan via the AC DC converter, because the TEC and also the fan are using a DC current. So the thermocouple will be placed near the TEC module, and it will give feedback to the PID controller about the current temperature or the perceived value. So the methodology that we are going to use to test our system is that the first one, we are going to test the TEC for its highest cooling capabilities without the heatsink at the cold side, because we want to test the minimum temperature that it can go. After that, we are going to test it for about 3 times and take an average of it as our final result. Each test will be run for an hour, and it will be sampled every 1 minute. The sampling is being done by recording a video, and we move the cursor from 1 minute to another minute. Okay, the next we are going to test the design system, which is the one with the fan and also the heatsink for the first minimum temperature, and then we are going to make changes if the temperature does not meet our requirement. Okay, now we move on to the results and the analysis. So this is our complete system. As we can see here, we have the thermocouple, we have the PID controller, we have the relay, we have the power supply, and also we have the heatsink, fan, and the peltier cooler. The one that we see in the slide is the hot side, which is on the outside, and there is another one on the inside, which is on the cold side. After testing the TAC module, this is the result that we get. The voltage draw is 12.12 volts. The current draw is 2.35 amps. The cold side, inside the insulated box, it can go until 7 degrees Celsius. The hot side, it can go until 44 degrees Celsius, and the delta between the two is 37 degrees Celsius. Okay, now we are testing the system heatsink with fan, which is our original design. As you can see in the graph on the left, the temperature cannot go lower than 24 degrees Celsius. So we need to make changes to our design. We think what might be contributing to the high temperature is that the fan itself is releasing heat into the system. So now we are going to make a system without the fan, but the thermocouple is going to be placed on top of the heatsink itself for the best case scenario. As you can see now on the right side, which is the heatsink without fan graph, as you can see, the lowest temperature it can go is until 15 degrees Celsius, which makes it more more usable than the ones before. So we are going to take the 15 degrees Celsius as our set value for our PID controller. And with PID controller, we can see that the temperature when we are using 15 degrees Celsius as our set value, the graph is very slow to reach the 15 degree Celsius mark because of the switching action of the PID controller. After we get our result, we can conclude our power draw, our energy draw, and our COP. Our energy draw is about, our power draw is about 26 watts. Our energy draw is about 0.3 kilowatt hour, and our COP is about 0.752. It is higher than the benchmark paper, so we have a success here. So this is the Gantt chart of our research activities in FYP1 and FYP2. So for the conclusion, our first objective, which is to design and to develop the PID control thermoelectric system, it is achieved because we can control the temperature using the PID controller. The second objective is partially achieved, which is this objective is to implement our design, because we have to make some changes. So you can see that it is partially achieved. And for the third objective, we want to, when we are comparing to our benchmark paper, it is be said partially achieved because we changed our design, so it cannot be considered as 100% achieved. So that's all for me. Yeah, so as for this is my reference, which is the number 2 is the benchmark paper for this project, which is from Fairuz Romeli. Okay, that's all for me. Thank you.